I think so, yeah. I think that yeah, I think that you yeah, so you can start a meeting and then oh, hey, then everyone can see you. That's just my ceiling. And then you can like you can stop the video. Um and then but you're still a part of the meeting. So you if there was other people in the chat, then you'd be able to see them and hear them and stuff. So um and yeah, anyway, we're gonna talk about Mclaren polynomials today. They're super cool, and I thought we could kind of just do sort of like an understanding kind of overview of it. So we're not gonna do too much like heavy lifting today. We might do a little bit, but I kind of just want to talk about what Mclaren polynomials are and why we have them and kind of like what they mean. So I'm gonna sort of switch back and forth between my iPad and my desktop. I'm gonna oops. What am I trying to do here? Yeah, so I'm gonna go back and forth so you can probably see my screen now. And we'll go into Desmos and then I'll go back onto my iPad. So it'd be great if you could follow along. Like if you oops, yikes. If you have the ability to use Desmos, I'd highly recommend that you do that because yeah, I mean the thing about Mclaren polynomials, like I remember learning about them in university, and I really struggled to understand like what we were doing and what this was all for. And just over the break, I was reading the chapter and kind of playing around with it, and it just kind of hit me. I was like, oh yeah, that's why we have these things. This is actually super useful. So I kind of want to start off by playing a little experiment. Oh, and by the way, we're gonna go until 2 o'clock today. I've made a few updates on my website. So check those for things like schedule and stuff like that, because I just want everyone to know like what the plan is. Yeah, we're gonna have 45-minute sessions. I'm just finding that like a full hour is a lot for me, just because like I'm constantly talking, and I don't think it's super helpful just like to be sitting here for an hour and just like listening to me talk. It's probably better if we just stick it to 45 minutes and then you spend the extra time working yourself. Excuse me. Yeah, so let's just jump right into it. So, oh, go ahead. Mm-hmm. Yeah, I still haven't received the test from everybody yet, though. So I do want to make sure that everyone has. Oh, am I? Oh, geez. I hope that wasn't happening in my other streams. I changed. Wait, because you guys are just hearing me through Discord. So that's weird that I would be. Huh. Hold on, let me just play around with the Discord. I tried to add a filter because I found that some of my what am I? That makes sense. I wonder if they unplugged it and plugged it back in, if that would help. Quantum internet, so it can both work and not work at the same time. Is this any better? Can you hear my voice at all better? Is it okay? Okay, so it was OBS. Okay, yeah, so let's say that we have a little black box, and a black box, if you haven't heard of it, is kind of a this sort of notion of like, imagine you found this little computer in the middle of the forest and you had no idea how it worked, but you could get it to do this cool thing for you. You just didn't know how it worked. So the idea of this black box that we have is that we can get we can take any function that we want, and we can feed it into the black box, and the black box is going to spit something out. It's like a computer, so it has an input and an output, and the output is such that it gives you this. So you choose some kind of, I guess we'll give it the function and some integer n. Actually, I should say a natural number n, because it has to be positive. And the idea is that it spits out the nth derivative of f evaluated at 0. Okay, so for example, let's try a few of these. So let's try like, let's say we gave it f of x equals, I don't know, let's do 3x cubed plus 2x squared minus 1. And let's say that we wanted the third derivative. Actually, let's do the second derivative. Let's say that n is equal to 2. So we feed this into the black box, and the black box spits out, well, I mean, we would have to actually do this ourselves, so let's quickly do this. So let's take the first derivative, so f prime of x, that's equal to, that would be 9x squared plus 4x, and then f double prime of x would be, well, the derivative of this, which would be 18x plus 4, and then we evaluate this at 0. So f double prime of 0 is, well, the 18 times 0 just disappears, so this is 4. So really what it's doing is it's taking a whole bunch of derivatives and then looking for the constant term. At least that's what it does if our function is a polynomial, right? So it kind of is looking at that constant term after you've taken the derivative a few times. So just to be clear, the black box would spit out a 4. Okay, so this is kind of the heart of what Maclaren polynomials are all about, is that we're taking derivatives repeatedly and then evaluating that derivative at 0. And oh yeah, you can't really see that 4. You sort of can. But the whole point of this is that we can get a lot of information about the original function using these little numbers that the black box spits out. So let's see if we can like reconstruct a function. Oh, did I disappear? Oh, shoot. Okay, hold on a second. Am I back? Did it come back? Oh no, here I have to select it again. Here we go. Aha, there I am. Okay, okay, where was I? Okay, so let's see if we can try to reconstruct our polynomial based on what the black box gives us. Okay, so let's start off with a polynomial like 2x cubed plus 3x squared plus x minus 1. And let's see if we can use the black box a whole bunch of times, and let's see if we could rebuild our original polynomial using the numbers that we get from that black box. Okay, so the first thing we're going to do, and this is, by the way, I should say that this is f of x. It's going to be really useful to us if we are naming our functions as opposed to just writing expressions down. Okay, so let's find what f prime of x is. So this is a new example. Yeah. I'll write e.g. just so you can be sure. Okay, there we go. e.g. Okay, so this is a new example. Okay, so the black box, you get a function. You take a function and you also choose a positive integer n. In this case, we chose n equals to 2 because we took the second order derivative. So that's f double prime. That's what the 2 was 4. So what we're going to do is we're going to use this black box several times. And so we're going to say n equals 1, n equals 2, n equals 3. So the thing about a black box is that you can use it several times. You can use it as many times as you want. It's like you have this cool little computer that you found in the forest. You can use it as many times as you want. The only thing is that you don't necessarily know how it works. But I mean, and I guess in our case, we know how it works. It's just, we're just taking derivatives. Okay, so let's find f prime of x. So that's going to be 6x squared plus 6x plus 1. And then f double prime of x is equal to, and we'll just take as many derivatives as we can until the whole thing is just equal to 0. So we'll kind of exhaustively take a whole bunch of derivatives, and then we'll evaluate all of them at 0, and then we'll see what happens. So this next one here, I'm going to get 12x plus 6, and then f triple prime of x is equal to just 12, and then the fourth derivative, so f, I guess we can call that the fourth derivative of x, it's supposed to be of x, yeah, I know, is equal to 0. Okay, so, and any derivative after that is still going to be 0, as we know. But that's still not what the black box spits out, remember? So we're going to evaluate each of these at 0. So f of 0 is equal to -1. F prime of 0 is equal to +1. F double prime at 0 is equal to 6. And finally, f triple prime of 0 is equal to 12. And if we really want, we could say that the fourth derivative evaluated at 0 is equal to 0. Okay. So we can so we've got these numbers. We've got these 4 numbers. It's also no coincidence that we have 4 coefficients, right? We've got a coefficient here, a coefficient here, a coefficient here, and a coefficient here. And I wonder if there's a relationship between these numbers here and these coefficients over here. And I guess technically this is not a coefficient, this is a constant. But I think you... Yeah, there's a factorial going on, and we'll see where that comes from. So like, sure, there's a 12 here and a 12 here, but I don't see a 12 anywhere in here. So like, we've got all these derivatives and everything, but remember, our black box doesn't tell us about the derivative. It just tells us these numbers, right? So we would only get these last numbers. So let's see if we can take these numbers and punch them back into the expression. So this one here is definitely going, this first one here, this is definitely our constant term, right? So that's kind of given already. This one here is, this is our coefficient on x, so that's like our linear coefficient. Yeah, times 1. Yeah, times 1. This one here is going to be, well, there's a 3 here, but then the reason it became a 6 is because we multiplied it by 2, right? So when we took the derivative, so it's our coefficient on x squared, and let's say multiplied by 2. Multiplied by 2. And then this 12 here, you can probably see where this is coming from. So this 12 came from over here, and this became 12 because it started off as 2, right? And then when we took the derivative, we had to multiply it by this 3. And then when we took the derivative again, we had to multiply it by 2. And then we multiplied it by 1 to finally get the 12. So this is the coefficient on x cubed multiplied by 3 times 2. And I guess I could say times 1. And this one too, why don't we call this times 1. And this is, of course, 2 factorial, and this is 3 factorial. So, oh, I wonder if you can see that or if my face is covering it up. Can you see that, or is my face covering it up? Oh, yeah, it's kind of covering it up. There we are. Okay, so where are we going with this? So let's see if we can kind of come up with some sort of formula, and the formula is actually already been made for us, but we're going to sort of use this as a basis. Yeah, go ahead. We got a question? Factorial. Yeah, this is a factorial. I don't know if you can see that. Maybe my face is covering it or something. We're okay, so it's that 6, right? The original one was 3, yeah. And then it became 6 when we took the derivative, right? Because you multiply by the exponent. So we did 3 times 2. And then we got 6, right? But it's 6 times x. And when you take the derivative of that, well, you would multiply it by 1 because there's an exponent of 1. So you multiply by the exponent. 6 times 1 is 6, and that's where that comes from. So this 6 is right there. Does that make sense? Okay. Okay, great. Okay, cool. So from this information, I'm hoping that we can see that we get these factorials for each of these exponents, because each time you sort of get closer and closer to bringing a coefficient into a constant, because the only way you're going to get anything to show up is if it's a constant, right? As soon as you don't have any more constant terms, then when you evaluate your function at 0, you're just going to get 0 again, right? So the only way to get anything is to bring it down from a coefficient and get it closer and closer and closer to a constant by taking the derivative. And each time you take the derivative, you have to multiply by an exponent, and then the exponent will come down. So you're going to have to multiply by the exponent, then 1 less than the exponent, then 1 less than that exponent, right? So that's where the factorial comes from. So if we wanted to, we could take this original, or this these series of numbers that we got from the black box, the -1, the +1, the +6, and the +12, and we could use that and reconstruct our original function back by saying, okay, well, first of all, I'm going to say A1 is going to be equal to, actually, let's call it A0, like A0. So A0 is going to be this first one. It's going to be f of 0. A1 is going to be f prime at 0. A2 is going to be f double prime at 0. And A3 is going to be f triple prime at 0. And this one is -1. We've got +1 after that. We have 6 after that, and we have 12 after that. So the way we can reconstruct this is, well, let's start off with this third term here, A3. So we're going to start off right over here, and let's see how we can get back to the original one, which was 2. So the way we do that is that we would take our original term, which is 12, and we would divide it by 3 factorial, and then multiply that by x to the power of 3. Now let's focus on this term here. So I'm going to have our 6, that's the term that we get, that's our A2, and we're going to divide that by 2 factorial, okay, and multiply that by x to the power of 2. Next up, we've got A1. So I've got 1 over, well, we could divide it by 1 factorial just to extend the pattern. And we'd have x to the power of 1. And then finally, this last one here, we're going to get, well, A0 is -1. And we'll divide that by 0 factorial. And if you didn't already know, 0 factorial is equal to 1. And we'll multiply that by x to the power of 0, which is also equal to 1, but that just extends the pattern. And when we do that, you'll notice that we actually get our original polynomial back. So 12 over 3 factorial, that is 2. So we've got 2 times x cubed plus, well, 6 over 2 is 3, so I've got 3x squared. 1 over 1 is 1. Let's actually just write x. And negative 1 over 0 factorial times x to the 0, that's just negative 1. So that's the original polynomial that we had, right? It was 2x cubed plus 3x squared plus x minus 1. Okay, so using this black box idea allows us to take all of these values that we get from taking the derivative of a function and evaluating that derivative at 0, and we can actually reconstruct the original polynomial. Okay, the thing is, we could do this for functions that aren't polynomials. So if it is a polynomial, then you can completely reconstruct the polynomial, like perfectly. So what I'm trying to say is, like, if I gave you a whole bunch of values and I said, oh yeah, these values came from this black box, and I got the so basically what they are is they're the function with a few derivatives taken of it, evaluated at 0. Well, you could go and reconstruct the original polynomial back in the way that we did, by dividing each of these by a factorial, and then multiplying it by x to the power of whatever factorial you divided it by. But it's more interesting when we actually do this to functions that are not polynomials. So I thought what we could do is try doing this for a function that's not a polynomial and see what happens. Are there any questions before we do that? We could do sine. Yeah, we could absolutely do sine. I was thinking of doing the exponential function, but yeah, let's do sine. Let's do sine of x. Okay, so, and I'm still hesitating to define anything. So we'll do sine of x, and then we'll talk about what the Maclaren polynomial is. Okay. So let's do this process. And how many times do we want to do this? Like 5 times? 6 times? Because you can't do it forever, right? Like, we have to stop at some point. Let's do it 6 times. We'll do it 6 times. Okay, so let's do this process to sine of x 6 times. Okay, so first of all, I'm going to say f of x is equal to sine of x. I'm just going to write x. Okay, so f of x is sine of x. So f of 0 is equal to 0. Nice. Okay, next up we've got f of x, f prime of x is cos of x. Okay, and so that means that f prime of 0, well, what's that going to be equal to? Well, I've got cosine of 0, that would be 1. Great. Now I'll do f double prime of x, and that is equal to negative sine of x. Okay, that's good. And so f double prime of 0 is equal to, well, negative 0, or just 0. F triple prime of x, that is equal to, well, the derivative of negative sine of x is negative cos of x. So f triple prime at 0 is equal to, well, 1, except now it's negative, so I've got negative 1. Now I've got the fourth derivative of x, and that is going to be back to sine of x. So f, the fourth derivative evaluated at 0 is just going to be 0 now. And you can probably see that we've kind of got a cycle going now, right? That now we've got sine of x. That's the same thing that we started with. So I'm just going to save us a little bit of time, because we've decided that we're going to do it 6 times. So that leaves me 2 more. So the fifth derivative evaluated at 0, that's going to be this one here, which is 1. And the sixth derivative evaluated at 0, that's going to be the one right after that, which is 0. Okay. So if I were to sort of reconstruct this, like let's say that we were given just these values. Like let's say that we were only given these values, but we knew that they were the derivative taken, like the series of derivatives taken at 0. Well, we could use that information to try to reconstruct the original function without actually knowing what the original function was. And we would do that by basically doing the same thing that we did with the factorials. So let's call this one p. I'm going to call this function p. P stands for polynomial, and I'm going to say that this is the 6th polynomial because we did this 6 times. Okay, so I've got p sub 6 of x is equal to, and I'm going to start at f of 0. So this is going to be, let's call this a0, let's call this a1, let's call this a2, let's call this one a3, a4, a5, and finally a6. Okay, so let's start off with the first one. So I've got a0, which is 0 over 0 factorial times x to the 0, plus, then we'll do a1, which is 1, over 1 factorial times x to the 1, plus a2, which is 0 over 2 factorial times x squared, plus, well, the third one, a3, is negative 1 over 3 factorial times x to the 3, and then the fourth one is 0, so I've got plus 0 over 4 factorial times x to the 4. The fifth one, where's the fifth one? There it is 1. So I've got 1 over 5 factorial times x to the 5. And that's probably getting cut off by my head. I guess I can just scroll up. There we go. And then finally, a6 is 0, so I've got plus 0 over 6 factorial times x to the 6. So we can simplify this, obviously. So the 0 terms we can just sort of ignore because they're just 0. And the other ones we can clean up. So this is going to be x, I guess it's just x, right? Because it's 1 over 1. This next one here is negative 1/6 x cubed. And then this last one here is 1 over 5 factorial. So what is that? 120? Yeah, I think you're right. I think it's 120. So plus 1 over 120 of x to the 5. Okay, so somehow we went from sine of x to this weird polynomial. So let's like, what does this have to do? What does this have in common with sine of x? Okay. Yeah, absolutely. So they've got the same derivative evaluated at 0, right? That's important, right? Because it's not so much that the derivative is similar, right? Because if I took the derivative of like p6 of x, like this polynomial that I just found, it would look quite different than the derivative of sine of x, right? However, when I evaluate that derivative at 0, that's where they have something in common, right? So it's not just the derivative, it's the derivative evaluated at a certain point. So now I'm going to take you off my iPad and bring you onto my computer screen. Can you guys see that okay? Yeah, okay. Okay, so let's first write sine of x. Okay, so that's going to be my f of x equals sine of x, something that we're all familiar with. And now I'm going to write just going to call it p of x. And that's going to be, what was it, x minus 1/6 of x cubed. Ooh, look at that. So already you can start to see that we have, like, this looks pretty similar, Like they're very close to one another. Let's add in that last term, the plus 1 over 1/20th of x to the 5th. And then now you can hopefully start to see what's going on here. Like we're actually getting very close to what that original function is, right? Like if I zoomed in here, like these look almost identical. Like they're the same function almost. So you can kind of see that I'm you know, making one invisible and turning it off and on again. So that's the power of this, is that just by taking a few derivatives, we were able to approximate the original function. And there's a lot of very big applications of this, because the thing about a function like sine of x is, well, honestly, it's not that complicated. But you can imagine some other functions that are much more complicated than sine of x. Functions that are so complicated that it would actually take a lot of computing power just to evaluate the function at a few points. But if you did know a few of the derivatives, especially those derivatives evaluated at 0, well, then you could approximate that function with a polynomial. And polynomials are very easy to evaluate because it's just like adding and subtracting and multiplying, right? It's very straightforward to evaluate a polynomial. Oh, oops. I'm just going to take you off. How do I do that? As far as I understand, yeah, that's how a lot of calculators would work. I'm not an expert on that, though. But yeah, I mean, the whole point is just that it's much easier to evaluate a polynomial than it is to evaluate, like, yeah, the exponential function or what have you. And what we'll see is that a lot of the functions that we know and love, like sine of x, cos of x, and e to the power of x, all of those have these little polynomial expansions that can be used to get a very close approximation of a value at a specific point. So we're going to explore those a lot in the next couple of days. So this is called the Maclaren Polynomial. So I'll quickly define it. So hold on just one second. Just want to make sure that I'm applying it properly. Okay. Okay, so let's define the Mclaren polynomial, and then we'll call it a day, and then we'll talk about the Taylor series after that. So so the Mclaren polynomial. Okay, so and it only works if you actually can calculate the derivative at 0, right? Like the absolute value function, you wouldn't be able to do this with because it has no derivative at x equals 0. So some functions don't work. But if a function f has n derivatives at x equals 0, then the Mclaren polynomial for f is, well, I'm going to call it p sub n of x, and that's equal to f of 0 plus f prime of 0 times x plus f double prime of 0 over, what is it, 2 factorial times x squared plus f triple prime at 0 over 3 factorial times x cubed plus, and we keep going, and we finally would stop at the nth polynomial, or the nth derivative, over n factorial times x to the power of n. Can you see that? Barely. Here you go. So this is a Mclaren polynomial. This is something that you have to memorize. I've also put a PDF on our website from Mr. McIntosh. So it's one of his, it's not so much like a worksheet, but like a explanation sort of document. It's really well written. I really actually like how everything is phrased. So I'd really like you to read that over. And I think there's a couple more things I wanted to bring up before we go. Yeah, so I guess this is sort of is a worksheet because there's some questions that you can do. So I'd like you to, I guess for homework, to read the first, let's say 7 pages of this PDF. And 7 pages sounds like a lot, but it's really not that much. I think, what is it, 1, 2, like 3 of the pages are just one example, and we've pretty much done that example, except we did it with sine of x. In this worksheet, it's e to the x. Yeah, and then there's a blank page, and yeah, so just read the first 7 pages. It's really not too bad. And then tomorrow we'll talk about the Taylor series, and that's where things get a little more interesting. We'll learn that the Maclaren polynomial is actually just a specific case of the Taylor series. So we'll leave it there. Are there any questions before I sign out? We're gonna go. We're gonna start at 1:15, and hold on a second. Who's John in the chat? John. Idea marked. Weird. Yeah. No, thank you. I think that on YouTube. Oh yeah, until it. Yikes. Sorry, I got distracted by that. I think a few people have been sort of hijacking my YouTube streams and kind of following the breadcrumbs into the Discord. What was your question again, Maya? Yes. Yeah, we're gonna go from 1:15 till 2. Yeah, that's the plan. Mm-hmm. Yeah. Yep. I'll tell you what my understanding of it is, and I think that everyone is still grappling. Yeah. So, okay. So I'm going to start off by rephrasing the question just to make sure that I understand your question, and also so that if you're watching on YouTube, you know what I'm talking about. So if I understand, you're asking, how is the rest of the year going to play out, especially with respect to our mark? Because I think his name is Radian Carter, who's like the... some person in the Winnipeg School Division sent home an email a little while ago. Let me see if I can find it. Where basically, yeah, like the worst mark that you can get is the mark that you had on March 20th, which was our last day of school. Let me see if I can just... come on. pull up that email. I think it was last week that it came out. Yeah. It was also emailed to your parents or guardians if you are under the age of 18, which isn't necessarily all of you. So you probably would have got it in your school division email as well. Yeah, I don't know where that email went. I'm just kind of scrolling through my emails now. But anyway, yeah, so the idea is that the lowest grade that you can get is whatever your grade was standing at on March 20th, or whatever the last day was that we were at school. My interpretation of this is, here's this John guy again. So yeah, my interpretation of that is that that's just like your lowest grade. So I'm just gonna keep on calculating your grade the way that I always have, but the grade that you had before March 20th is going to be the minimum. So you've got either two choices for your grade, and you'll get the higher of the two. The two options are your grade on March 20th or your grade as of whatever our last test got, and I'll keep doing that for the remainder of the year. The provincial exams are canceled, yeah. As for us, I haven't decided really, and I've been speaking with some of my colleagues, also Mr. Hutchison and some of the other teachers and principals have sort of been talking about what this all means. I would still like to have exams, kind of like, but exams in the sense that like what I gave you last week, so you kind of have a couple of days to do it. So yeah, that's kind of what I'm aiming at, is the idea of having well, I mean, we've already had I would call it like a test. If we're going to have a final exam, I don't think that we will have a final exam in this class, because you guys have the AP exam, and I think that that's more than enough to like for you guys to do. So yeah, we're not going to have a final exam, but I am going to continue to have like tests, but the tests are just going to be like what we did last week. So like a take-home test. So that's kind of what I'm getting at. Does that answer your question? Okay, perfect. Any other questions? Okay. Go ahead. Okay, keep in mind, just because someone is not here does not mean that they're not partaking in the class, right? Like my YouTube videos have some views on them. It's not like I'm trending or anything, but like I have often like a couple dozen views. Not so much in this class. I think I usually get maybe 4 or 5 views, but there's only so many of us in this class. So are you asking like if can someone just check out and get a grade? Well, yeah. I mean, if that's what you want to do, then yes, you can just have that. Yeah, I mean, like that's exactly it, right? Is that you still have to do the AP exam, right? And I think it's a really good idea to keep preparing for that. It's not going to be an easy exam, but I think that the payoff is going to be huge. Getting this out of your way. You put so much work into this all year, and it's what, 45 minutes of pain, right? You guys have endured far worse already. At school, I don't think so. As far as I understand it, you cannot have more than 10 people in an institution at the same time, and I'm not sure if that means like in the same room or in the same building. If you want, I could look into that. Are you concerned about your internet connection or anything like that? Yeah, yeah. Um, I can look into that. Were you saying something, Crystal? Okay. Yeah, I know that the College Board is looking into different ways of offering students extra support. It would be that technological support or what have you. I can look into that for you. But yeah, my immediate my gut instinct is that no, you cannot write it at school. But I can certainly look into it. I mean, maybe they would be able to say something like, well, if it's only a couple of students and everyone is in a different room, I don't know. I'll look into it. I certainly cannot say yes because it's definitely not my call, but I can certainly look into it for you. Yeah, no problem. Are there any other questions? No? Okay. Just so you know, I put another update on the website. I'd like you to read it if you haven't already. I think that the main thing is just like the schedule. So now we're going to be going from, what did I say, 1:15 to 2 o'clock. And like obviously there's going to be some like right now, like I'm going 10 minutes over. But yeah, the idea of it is that I want to kind of stick to 45-minute lessons. And something else that I put on there is just a little note about asking for help outside of class time. So it's great when you're asking for help, and it's really important that you continue to do that if you're stuck. That said, just because I'm home all day, it's really hard for me to draw barriers and boundaries between when I'm working and when I'm not working. So going forward, if you ask a question sort of outside of regular school hours, I'm probably not going to answer it until the next day. So I'm going to try to do all of my the main amounts of communication between 9 to 5 during the week. Now, of course, there's going to be exceptions to that, especially if it's something urgent. But if it's okay, I can't seem to get anywhere with question 3B in the text. I'm just gonna sort of let you struggle with it, and then sometime the following day I'll kind of respond to you. So just be aware of that. If you ask a question and I don't respond right away, it's not that I haven't seen it or that I'm ignoring you, or I guess I sort of am ignoring you, but it's a purposeful ignorance. So yeah, don't be offended. I'm just trying to sort of make this work for me in a way that doesn't make me super grumpy and tired and really resent everyone asking me questions. So if we can kind of just stick to questions during the day, then I'll just be glad to answer them right away. But if it's at midnight or something, I'm just gonna turn my phone off and talk to you the next day. So okay, so if there's no more questions, I'm gonna sign out, and I will talk to you tomorrow. Okay, take care. Bye-bye.